this afternoon. Fabio Pliga is going to be talking about, at 3:15, about really diving into the interactive component and building sort of bokeh apps, bokeh dashboards and stuff. So that'll be a really great segue this afternoon. So data. At the heart of bokeh is the model, the column data source. And it's very simple. It's just a table of data just like you might expect. And so, oh, that's not a good sign. OK, so we take a data dictionary in Python, a normal dictionary, keys, array, and we also, how many people here have worked with pandas? OK, almost everybody. If you haven't worked with pandas, it's fine. It's a lot like Excel, but way better in Python. And it's not a lot like Excel. It'll change your life. But you can, the core of it is you can pass it a dictionary and you get out a table of data. And there's lots of other ways you can read from Excel, from JSON, from CSV, and so on. If you haven't used pandas before, I would totally recommend Brandon Rhodes' pandas tutorial from PyCon 2015. It really boils down like how to really just understand it, but keeps it at a nice simple level. And so you can make your column data source from either a dictionary or from a pandas data frame. And your data ends up represented like that. And you'll notice the one difference between when I passed in my dictionary and when I passed in my data frame is that I've got this extra key value here. The index has come from the pandas data frame. It's this left index here that it's named index for us. So that is the column data source. The next thing that's at the heart of bokeh is the plot. And I'm skirting over some details here because I don't think they're that important. There's these models, plotting, charts, these three different ways to kind of use bokeh, but they have a lot in common, and you should find it pretty easy to jump between the three sort of levels, but I think it can be a bit confusing knowing exactly what to do from the get-go, which is why I'm trying to sort of show you all three. So at the lowest level, we have the plot object. The next level up, we have the figure, and finally, we have the charts. They're all different things. They come from different modules within bokeh, but you're going to see they all have the same kind of attributes attached to them, like a toolbar location, background fill, and so on. So once you're working with one, you can kind of reasonably assume that the other one's going to kind of behave similar. And they all have three really important methods on them: add tools, add layout, and add glyph. And if you can remember those three methods, you're going to get a really long way into building all of your plots. Glyphs, I hear you say. No one said glyphs. OK, glyphs, to me, the word means nothing. I was so confused for a long time. It just means shapes. And I don't know why it's called glyphs. I'm sure there's some very, very logical reason. But glyphs are just shapes. And so this is actually from the examples. And these are all of the different kinds of shapes that you can spell within bokeh, and in some combination of all of these, there's a whole other set here, in some kind of combination of all of these things, you can make pretty much anything that you could think of. If you couldn't, I'm sure we would add another one, but we really have got most things covered here. So glyphs are just shapes. So we're building a dashboard. We've talked about data. Let's talk about charts. But I keep going on about this models, plotting, charts thing, and I want to just lay it out a little bit more. So there's these three modules: bokeh.models, bokeh.plotting, and bokeh.charts. Bokeh.models is the lowest level of bokeh, but it doesn't mean it's a level you should be afraid of. It's an awesome level. I love to live in the models level. Everything above it is built on top of models. So it offers you the most control, but it does mean you have to do all the work yourselves. On the complete opposite end, you have bokeh.charts. These are one-line functions that let you spit out a bar chart, spit out a line chart, spit out a horizon chart. It just takes your data frame and gives you something awesome. So it's very, very quick to use, but it sort of does all the magic for you. Bokeh.plotting kind of lives in the middle, and you have to sort of organize your data for it, But it then tries to pick sensible defaults, so you don't have to add the axes and add the grid and so on. So it tries to sort of give you something you want, but it gives you a bit more control. Where you want to work is really a matter of personal taste. Personally, coming from a web world, I started with charts, and charts for me were a gateway to models. But I think a lot of people coming from the data science world find plotting sort of more intuitive. But you'll see them all, and you can, you can choose what you will. So let's start with charts. So this is one little pocket of the dashboard that I was demoing, and this chart here, this bar chart here, has come out of the charts interface. So one of the things about the charts interface is that it kind of does some magic. It just takes your data and spits out a chart. So you kind of need to know what it wants the data to look like, otherwise it can't do its magic. So often when I'm getting started with a chart, especially if I haven't used it before, I'll just set up some dummy data to make sure it's kind of roughly doing what I expect it to do before I put in my real data, because then, who knows whether it's bokeh or my data that's being weird. So we just have a simple thing here. We've spent some time with ponies and unicorns and other magic things. And now we get to importing our bar chart. And so we've imported it from the charts function. We import bar. And now we just call it with our data frame. And we show the bar chart. One line. And here we have our chart. We have zoom. We have reset. We can save it. We can do that. We can resize it. And this is a web object. You could share this HTML. It's all going to work beautifully for you. So that's working how we expect it to. So now we're going to try with some of our real data. All of the code that gets all the real data is in the repo that I shared with you earlier. I'm not going to cover how I made it today. This is the raw data, and then this is the sort of process data that I did. So once again, I spit out my data. I spit out my bar chart, which is almost how I want it. So now I'm going to add a couple more options. I'm going to stack my bar chart, and I'm going to set a palette. And now it's starting to look a lot like what I showed you earlier. Styling is later in the talk, so we'll get to that in a bit. So there we go. One line, bar chart. It's interactive. You can add hover. You have zoom, and there you are. What I forgot to put in was a list of all of the different kinds of charts that you can import, but at the moment it's all the ones you might expect: line and time series and horizon and scatter and so on. So next up is I/O. What you might have seen me do at a couple of the top of those notebooks is from bokeh.io import output notebook and show. And when I call output notebook in an IPython notebook, I see this bokeh.js successfully loaded. So that's how we work with bokeh in a notebook. And then there's also this output file, which is the sort of equivalent. And so then at the top of my notebook, I would call output file, and I would give it an HTML file name. And then when I hit show, instead of showing in the notebook, it opens a new browser with my static HTML has been saved, and I could share that with somebody. I like to use this extra argument mode equals CDN, which instead of dumping all of the JavaScript and CSS that power bokeh inline into the HTML, it just puts in a reference to the bokeh CDN, which takes your HTML from sort of 1.6 megabytes down to about 6K for a small plot. So it's a decent bandwidth saver. So that's how you get started with spitting your stuff out. So plotting. We've done the charts interface, and now we want to look at the plotting interface. This is a plot that I couldn't build with the charts interface. There isn't a chart that's sort of pre-baked for me that does this. I have this categorical axis on the left side here, splitting up the different kinds of activities that I get up to. I have a time series axis on the bottom here, and then I have these rectangles that I've plotted across. So once again, I'm going to try with some test data first. This time, I'm going to build my own column data source. You notice I didn't have to do that with charts. I just threw in a data frame, and it just spat out a chart. But this time, I am going to have to build my own column data source, and I'm going to do it by passing in a dictionary. And then I'm going to instantiate my figure. Now, figure doesn't do anything on its own. In fact, if I just do show P here, what I get is a very helpful error message that's just come into bokeh saying, you have no glyph renderers, I'm not going to be able to plot anything interesting. So we're starting to, this sort of validation and error helping is new, and so it's a bit spotty. So there are some bits that do it and some bits that don't. So if you ever see a place where you're like, oh, why didn't it give me an error message? You know, just throw up an issue on GitHub, because we keep adding these in. So once we have our sort of empty figure, now we have a whole bunch of methods on it. Remember all of those different glyphs that I showed you over and over and over again? For every one of those glyphs, there's a method. So there's p.quad to plot a quad, there's p.rect to plot a rect, there's p.circle to plot a circle, and so on and so forth. And so for our one, we're going to use the quad, what do you call it, method, and spit out a plot. This was just dummy data, so I just have linear axes on the left and bottom here. And so now let's think about how we might do this for our plot. So here's our data. We have the start and the end in time of each of our blocks of time, and then we have our categorical name for our label for each of those time blocks. So we're going to try plotting this. And it's not looking great. It hasn't given us anything. And if I open the console, what I'm going to see is, although I tried to pass it some data, and I really did try, if I open the console, it's going to say, could not set initial ranges. And if you're thinking, opening the console, really? This is where these requests for more validation can come in. Like, this is totally something that we could have put one of those error messages in for. We haven't done it yet, so we should do that, and I'm sure it will come. But going to the console is always a good place to look if things didn't work how you expected to. So what happened was, instead of, if I had linear data, like I had up here, just a series of numbers, when I instantiated my figure, it was clever enough to figure out that, okay, I can figure out the ranges, this is no big deal. But when I passed it my data with time and categorical axes, it's like, I don't know what you want me to do here. Like, you've got to give me some help. So now when we're instantiating our figure, we are going to specify the range, the time series, and we're going to specify the categories on the left side. When we do this, we get out something that looks pretty good, but not quite right. What you can see is our little blocks of time are like teeny tiny. I don't know if you can even see that at the back, but they're there, but they're just really small. And so what happens is, how do you specify height on a categorical axis? This is a bit of a tangent, but it's a good one to know. So when you have time, or 0 to 10 or whatever, it's pretty obvious how you specify height or width. When you have a categorical axis, what does that mean? And so the way we do it in bokeh is from like the left to the right of your categorical axis, or the bottom to the top, is 0 to 1. And so you append a colon to your label, and you add like 0.1 for the bottom to 0.9 for the top, or the left or the right, or whatever. And so once we've done that, if we try again, now it's come the height we expected to. And so if I change this to be 0.4 to 0.6, they'd be much narrower, and so on. So you can play with that as you wish. And one of the things you're seeing here is, think about that original data frame. That original data frame, the chart that I showed you, was essentially a switched around version of this. The chart function did all of that magic for you. It magically figured out how wide I'm going to make things. It processed all the data, set that all up for you so that you didn't have to think about it, which is awesome until it doesn't quite do what you need it to do, and then you have to do it yourself. And actually, to be honest, one of the ways I learned bokeh was I started using the charts, and then I went and read the code for the charts to figure out how it was doing it all, and then I was able to build my own. So there we go. Okay, so that was plotting. A little bit more verbose, but a lot more control. You can do lots of different things there. And so last but not least, we get onto models. And so this is where we use the lowest level of bokeh to build up our charts. In the docs, I'm pretty sure I read somewhere that it's like, most people wouldn't need to do this, but I like living down here, so, but each to their own. So once again, I've pre-processed all my data, and I've made a a dictionary of data sources that I want to that I want to plot, which looks something like this, which is nice. So so this should look somewhat familiar. This is our first attempt at making a plot, and this should look a lot like what we just saw in plotting. We are specifying the x range and the x range and the y range, because if we don't, bokeh will freak out. Now, instead of, we're not calling a method just yet, we're actually specifying our line here. So when we specify our line, we've imported line from bokeh.models, and we're saying, I want the x to be powered, if you like, by this column called timestamp. I want the y to be powered by the column called cumsum hours. And then what I'm going to do is I'm going to loop through and I'm going to add lines for each of my data sources that I want to add. So it's allowing me to add lots of different lines. And so to do that, I use that add glyph method that I talked about before, and I pass in a column data source, and I pass in the specification for my line. So when I do that, this is what I get, which is what I asked for, but is not beautiful. And that's because down at the models level, we really do have to spell everything out. So the first thing we might want to spell out is some color. And Bokeh has a whole bunch of built-in palettes for you that I would totally recommend using as defaults, but you can, of course, spell your own palettes. And palettes are just a list of either hex or IGBA tuples or a whole different bunch of things, and you can see the reference at the palettes documentation. So let's try again with a little bit more style. Again, we just have our ranges specified. Now we're going to try a bit of background fill, a bit of border fill, sort of mess around with this. And now we're going to add some layout. So this is where we're adding our linear axis on the left and our date time axis on the bottom. And then now our line, the specification has got a little bit more complicated. We're not only specifying the x and the y, we're specifying a color, we're specifying some line width and so on. And then once again, we're just using this add glyph method, use the source, that's how I use the force, use the source, and add the line. And once we do that, things start to look pretty promising. And so we can really start messing with this. So if I just turn this into a method so I can make it nice and repeatable. And now what I've done is I wanted to add, so this has no tools on it, right? The charts and the plotting came with all those tools just poof out the box. Now we have to manually add the tools ourselves. To do this, it's very easy. You just use add tools and you specify the tool you want to add. And now we have pan added, and that's awesome, except I don't really want it to pan up and down because that doesn't make any sense for my data. So I'm going to try constraining it. So constrain equals width. Oh, that didn't work. That's weird. What happened? Oh, thank you, Bokeh. It has told me that constrain is an unexpected attribute, and the things that it's expecting are dimensions, name, plot, session, or tags. And so this part of the error reporting of Bokeh I find incredibly useful. If I can't remember what it wants, I'll often just put in garbage so that it tells me what it's expecting, which is really handy. So it said it wanted dimensions. So, oh, whoa, IPython fail. Oh, I think I just deleted my cell. Hang on. No, where did it go? Oh, it's there. Thank you. No, I changed it to Markdown. There we go. So it said it wanted dimensions. I think it said that. It did say that, but now it's saying it got an unexpected error. And it's looking for a list, and the list has to either contain width, height, x, or y, but it just got width, it didn't get a list. So again, there's the properties reporting, and then there's this value reporting, which is part of what we use to help us be able to serialize from Python to JavaScript, but it's also a very helpful for debugging your code as you go. And now, huzzah, it pans left and right, and I can't go up and down however much I might want to try. So we can keep going and going with that, but I will spare you for now. So, quick mention of the examples in the bokeh repo. So there's the gallery on the website, but if you actually download the repo and find the examples directory, there are just a bajillion examples in there, and in particular for getting started with models, they're incredibly helpful, so I would totally recommend just downloading them and running them. So, styling. We started to see a little bit of that just now on the models, but styling is possible for every single level, for plotting, charts, models. It just depends on how you want to do it, really. So I'm going to show you for charts and models, and you know, take your pick. So in the interest of time, I'm going to skip the little prototyping. But this is us making a bar chart, just like we did earlier. And once we've got that, we can then just start to set all of the attributes, the toolbar location, the background fill, the outline, and so on. We go and we grab the glyphs, and we can specify their fill color and line color. And we set the attributes, and we set the attributes, and we set the attributes, and then finally we show it, and it looks gorgeous. And so when you're in the IPython notebook, you know, one of the nice things about it is the autocomplete, and the fact that you can really sort of use IPython notebook to sort of help you see what the attributes that you might have available to you are. And so that's one of the ways that, especially early on, I used to play around with bokeh a lot. Now, with models, we spell it all first, right? We don't create something and then fix it. We spell it all as we go. And so what I like to do is, and the other thing we like to do, if we're making lots of plots and we all want them to look the same, is we can start to build these dictionaries of properties, like our line colors and so on, and we can just splat them into all the axes, or we can splat properties into all of the plots. So I build up this, I typically build up this style sheet, and the top of the style sheet I'll have my colors and padding and things like that will sort of mirror my CSS if I'm building a website, and so that I can sort of have those common colors and things like that across. And then I have this plot properties dictionary, axis properties dictionary, and so on set up in my in just a file called constants. And then when I come to build my plot in models, it actually starts to look quite clean. I just make a plot and I put in the plot properties. I make my two axes, they share all these common stylings. Again, I make my two rectangles, they share all these common stylings. And so this is why I kind of like working with models, is because I'm doing a lot of heavy customization typically, and I find this fairly clean as opposed to that big sort of quite verbose version that you end up doing where you fix all the attributes on a chart. But each to their own, anything is possible. So, layouts. If you're just working within bokeh, you're not interested in putting stuff on the web, there's plenty that's sort of in the box to help you make something nice from the get-go. In particular, there's hplot and vplot that are in bokeh.io. And what they do is they just kind of make rows and columns. And it's pretty self-explanatory. So we've got here a vplot, and we've nested inside it an hplot and two charts. So our hplot across here, we've sort of lined up our three things. This is not my dashboard. This is just sort of giving you a demo of what you could do. And then I've stacked it on top of some other plots. And so you could spit that into an HTML using the output file method, and you're going to get something that's pretty presentable. And all of these all of these plots can interact with each other once they're in the same document together. If you spell it all in a nested thing like this, all of those things will be able to interact together. Because I typically sit in the web, I use, if that's the very high level, I use the very low level embed function. And again, to use this, I use the components method, and I take a dictionary of all of my plots, and what the components method gives me back is my HTML script and a dictionary of all of the divs that I have to, the div tags that I have to stick into my HTML. So I'll take a template. This is a very simple one where I've just imported bokeh and maybe some CSS at the top, and then I've started to template in the divs that bokeh has given me back, and I template in, very important, my script. And using that, rendering that out with the context of the script and the divs, which if you're in, this works in Django, Ginger, whatever your templating language is, it's all the same. Bokeh comes with Ginger built in, so that's kind of convenient. You can start to build, this is an HTML page, right? I had H1 building a dashboard, my time selector, and this is the actual HTML page that I could either be rendering through a web application or as a static HTML. So that's layout, and I'm pretty sure Fabio is going to talk a bit more about embedding and stuff in more detail later. So if that was too fast, there'll be more. And so with all of that under your belt, I promise that adding to it the pandas data frame method to HTML, which turns your data frame into a nice HTML table, you can make everything that you see here. These tables here are pandas tables. This is our plotting plot. These are our bar charts. These are our line charts. And we've got it all with a nice, and what's different about it is I've used a nice template. I've used some nice CSS, and it all comes out very nicely. So last but not least, interactive. So there's two parts of interactive. The first part has been built into Bokeh for quite a while. We have our tools like hover, select, zoom, pan, which we've been talking about a little bit, and the shared selection and panning. So I'm going to quickly run through how to do that. So just getting started, I have a simple set of data. And the first thing I'm going to do is I'm going to share some ranges. And so what I've done here is I've got a figure. I've got three figures, sorry, that I've sat side by side. And in the second figure, I've used P1's X range, right? And in the third figure, I've used the P1's X range and its Y range. And so when I do that, it means that if I pan left to right, it's going to pan out on all of the plots. When I pan up and down, because I only shared the Y range with one other plot, only one is changing. So this lets you sort of, there's lots of different times when you might be wanting to see different dimensions and how they compare. So you can plot different dimensions on different plots, but start to move around in sync, which is very handy. The other thing that we've done here is we've shared a source across them. So instead of making different sources for different plots, I use one source with all of my data in it, and I shared it across my three different plots, but I plotted different things. So my left plot has X and Y naught, my middle plot, and so on. And so once I've shared a source, when I start using selections, when I start using selections, they'll share across all the different selections. I'm running a bit low on time. I'm very sorry about that. This is the spelling for how to do hovers, which I'm not going to talk about. I'm going to whip through interactions to show you. So this is a quick example of something very nice I did with linking selections. So when I click on a country, this number here the name of the country updates, the value updates. When I click over on this other tab, I've also shared it across tabs, and so Mali has updated here. When I click on Ghana, if I go back to my first tab, Ghana will still be selected. So that's a bit more sort of sophisticated example of what you can do with that linking. And last but not least, I have 4 minutes and 14 seconds to whip you through callbacks, and then Fabio is going to really take this and run with it this afternoon. So callbacks have just been added to Bokeh, and they're super awesome. They allow you to write a tiny piece of JavaScript or a giant piece of JavaScript if you want to, but you write some JavaScript in your Python code, and you can start to do really sophisticated interactions. And they're currently available on a sort of weird and somewhat ad hoc subset of all of the components of Bokeh, and that's the list there. And as a web developer, I really love this because what I really want is that really rich kind of experience. Nothing crazy fancy, not doing sort of computation on the server or whatever, but giving people the chance to really play with their infographic a little bit. And this has really allowed me to do this. So this is one I built recently. They've got this slider at the bottom. This is a Bokeh slider. And what I'm doing, it's very simple. Whenever I slide, the value of this number at the back here changes, and the data source that powers these circles sort of switches out. So this is something that is a completely standalone piece of HTML, all done in Bokeh, using this new callback mechanism. if you hate JavaScript more than life itself, we're starting to, in the same way that we made charts as these sort of canned one-liners that will sort of do all the magic for you, we're starting to build up these actions. So a common thing might be you select a glyph, and a URL opens. So the first action we've made is open URL, but there'll be more sort of pre-built things, so you never have to write JavaScript coming. Here is an example of how to use the callback. Excuse that typo where it just says code equals blank there. So let's say that we make a callback, and we have some code like change the selected value to a new thing. And now instead of just adding a tool, hover tool, we add it with our callback. What's exciting here, and is a little hard to see, but when you get used to it, you realize how magic it is I've passed in these arguments. And what I've done is I've given a name, my column data source, and I've passed in the Python object. So now in my JavaScript code, I can use my column data source as a JavaScript object, and I can start playing with it. And it's like I was playing with my Python object. So you don't have to do any magic. You can sort of be playing with your Python objects in JavaScript. And if you use that components method, where you just have them all in one components method and all in one script, that's how you can start interacting across all of your different plots. And Fabio is going to show you all about that later. So, with 1 minute left, are there any questions? Yeah? Yeah, you can shout. I can repeat it. Yes? You mean like a Google map or a OpenStreetMap or whatever? Oh, sorry. The question was, can you embed a Google a Google map or an OpenStreetMap or something like that? There is actually a Gmap plot, like bar chart or something like that, like a plot that you can instantiate, which works okay. But we wanted to make it better, and one of the things that I'm meant to be doing this summer is actually working on our mapping support in general, which is not as hot as we would like it, but it's really high on my to-do list because it's something I want to see done. So, yeah.
As Sarah told us in the afternoon, we have the possibility to learn a little bit more about Bokeh. So I want to thank you for your talk. We have now We have now 5 minutes break, and then Sever Baneshu will talk about some workflow apps.
Hey, how are you? Oh, that was loud. Thank you. Are you speaking next? No. Miroslav? Okay. How's it going? Nice to see you. 2 days a week. I still work at the non-profit in Cambridge. I still work there 4 days a week, so most of the time I'm still there. But then I really love Bokeh, so they hired me on to work a little bit on it.
That is awesome. Hi, can I ask a very quick question?
Yeah, of course you can.
If you've got some data that you don't want anyone else to see, it's confidential, but you do want to display some visualizations on a corporate intranet, let's say.
Yes.
Presumably I couldn't use that HTML thing that you showed, because that's sending the data outside, is it, to render the...
No,
it's not?
No, it's completely, it's not Tableau, Plotly bollocks.
Okay.
It's totally, mic's not on. It's totally...
We're still broadcasting online, are we? Yeah.
No, it's totally, no, I really am not a fan of that at all.
Right.
So
it's all done on your machine? Right. Okay, cool.
Yeah.
Thanks a lot.
No worries. Are you still at Anglia?
Yes.
How's it going?
It's going very well. I was doing computer vision, and that's gone awesome. Taking on a new job at King's College London doing coding tools. So
Doing what?
programming tools, visual programming.
Oh, cool.
Merci.
Sorry. Sever.
Yeah.
Okay, hi, I'm Miro.
Hello.
I will try a little bit help you and present you a little bit. Where you come from?
Romania.
I thought. Yes. Okay. After the Baneshu?
Yeah.
Baneshu. Okay. Should I present something before? Tell you some.
No, nothing.
Nothing. Okay. At the end, you have you know the time. I will show you 10 minutes before, 5 minutes before. Do you want some questions and answers at the end?
I try to, but I'm not sure if there will be enough time. We'll see about
Okay,
that. I
okay.
try to accommodate for that.
Sorry, my boss. Okay.
Because we had major problems with others coming in late, and they were sitting on the sides and had to do the dodge. Yeah?
We have 1 minute or so. I think I see quite many green chairs in the middle. Could you move a little bit to the center of the room, please, so that if other people come later and want to sit down, so they don't have to climb over? Môžete sa troška poposúvať, aby v strede bolo tak troška vyplnené? Merci. OK. Alors, les gars qui sont des côtés, peut-être vous pouvez vous bouger un peu vers le milieu, aux places qui sont vides. Könnt ihr euch bitte in Richtung Mitte bewegen? So, Sever Baneshu is going to speak about distributed workflows with Flowy.
Thank you. Hello, everyone. Thank you for joining me. My name is Sever, and this presentation is about a library that I'm working on, and which makes it easy to model and run distributed workflows. There will be a Q&A section at the end, hopefully, if there is not enough time. You can also stop me during the talk and ask me questions if anything is unclear. Okay, so let's get started. We'll start by discussing a bit what a workflow is, and then I will show you a quick demo and spend the next part of the presentation trying to explain what happened during the demo. So the term workflow is used in many different contexts, but for our purpose, a distributed workflow is some kind of complex process which is composed of a mix of independent and interdependent units of work that are called tasks. Usually, workflows are modeled with DAGs, which stands for directed acyclic graphs. Think dependency graphs between the tasks. And they are modeled using some domain-specific language. Or with ad hoc code, like when you have a job queue, but what you really try to accomplish is to have an entire workflow, and you use the job queue and the tasks in the job queue to do some work, but also to schedule the next steps that should happen during the workflow. Neither of those provide a good solution And the reason for that is because DAGs are too rigid. You cannot have dynamic stuff happening there usually. And the ad hoc approach, where you have the job queues, tends to create code that is hard to maintain because the entire workflow logic is spread across all the tasks that are part of the workflow. Another problem with the ad hoc approach is that usually it's very hard to synchronize tasks between them. So if you want to have a task started only after other tasks are finished, that's usually pretty hard to do. Flowy takes a different approach for the workflow modeling problem, and it uses single-threaded Python code and something that I call gradual concurrency inference. Here's the toy example of a video processing workflow. At the top, we have some input data, and in our case, there are two URLs for a video and a subtitle. And then there is an entire workflow that will process this data. And what it will do, it will try to overlay the subtitle on the video and encode the video in some target formats. It will also try to find some chapters, some cut points in the videos, and extract thumbnails from there. And we'll try to analyze the subtitle and target some ads for this video. So the interesting thing here is, and it's something that you cannot easily do with DAGs, is the part where the thumbnails are extracted. This is a dynamic step, and the number of thumbnail extraction tasks can differ in video. So this is where you need some flexibility. So next, I would like to show you how this workflow is implemented in Flowy, and then, like I said earlier, I'll try to explain what really happened there. So let's see. All right, so I start with the activities, or rather the tasks. And in this case, I'm using some dummy tasks. You can see all of them have some sleep timer in there. They are doing something, and they are regular Python functions. There's nothing special about them. They just get some input data, do some processing, and output a result. So this is similar with what you will get in Celery or a regular job queue. This is the workflow code. So it's the code that would implement the workflow that we saw earlier. Again, it's regular Python code. We are just calling the tasks, but there is something funny about it because it has a closure, and we are not importing the tasks, the task functions themselves. And there is a reason for this. This is a kind of dependency injection, and there is a reason for it, and we'll see later why this would be useful. Other than that, there are just function calls and regular Python code. Actually, I'm going to demonstrate that this is not anything special by running this code. So what I do here, I import all the tasks and the workflow function. I'm going to pass the tasks to the workflow closure and then call the closure with the input data. and this will run the workflow code sequentially. I'm also going to time this execution. So it will take a while because of the timers that I have there, forcing the task to sleep. And hopefully, yeah, that's what happens. Sorry about that. I'll try again. All right. I don't know what's going on, but whatever. Yeah, something's wrong. But so usually it should work with. It's just regular Python code, so there is no reason for it not to work. But yeah. But the interesting part here, so running that code would take about 10 seconds because of all the timers, and everything will happen in sequence. So the interesting part is being able to run this as a workflow and have all that concurrency happening. So I'll try to do that. Okay, so it went much faster, about 2 seconds. And the reason for that is because all the tasks that could be executed in parallel were executed at the same time, as we can see in the diagram that was generated. So the arrows there represent a dependency between the tasks, and we can see a lot of them were being executed at the same time. So I'm going to try to explain how that works and why it went so fast versus the previous version, which didn't work. Right. So in order to understand what was happening during the demo, I have to talk about workflow engines first. And we begin with a simple task queue where we have all the tasks that we want to be executed. The workflows are pulling the tasks from the queue and are running them. And as I said, when you have an approach similar to this, there must be some additional code in the task that will know to schedule other tasks when they are finished. So they also generate other tasks beside the usual data processing that they are doing. And this is not very good because the workflow logic will get spread. And like I said, it's also very hard to synchronize between different tasks. So another idea would be to have the tasks generate a special type of task called a decision. And what a decision does, instead of doing some data processing, it will only schedule other tasks in the queue. So it acts as a kind of orchestrator. Like we can see here, the arrow from the storage to the worker is reversed because the decision will read data from the data store in order to try to get a snapshot of the workflow history and the workflow state. And based on that state and all the tasks that were finished, it will try to come up with other tasks that must be executed next. But this solution is also not very good because you could have concurrency problems. So if two tasks finish one right after the other, you can get two decisions scheduled. And if those are executed in parallel by two workers, they will generate duplicate tasks in the queue. So this is not a perfect solution. So in order to improve this even more, we need to have the queues managed in a way that all the decisions for a particular workflow execution will happen in sequence. And for this, we introduce another layer that will ensure this. Another thing we would also want to add is some kind of time tracking system that will know how much time a worker has spent running some tasks. So, and it can declare the tasks as time out if a certain amount of time passes without the worker doing any progress. So this is not something new. This kind of workflow engine is implemented and provided by the Amazon SWF service. It's also available as an open source alternative in the Eucalyptus project with the same API that Amazon has. There is also a Redis-based engine similar to this in the works that I know of. And there's also the local backend that you saw earlier in the demo. And the local backend will create all this engine and the workers in a single machine on a single machine, and will run them only for the duration of the for the duration of the workflow, and then everything gets destroyed. So hopefully by this time, this was the code that the workflow code in the demo. So hopefully at this time, you kind of get an understanding that this code will run multiple times. So every time a decision needs to be made for this workflow to have progress on it, this code will be executed again. So if I were to put a print statement there and run the workflow, I will see a lot of print messages. Okay, so I mentioned earlier about the dependency injection and why that's needed. And the reason for it is because Flowy will inject some proxies instead of the real task functions. And the proxies are callables and will act just as a task would, but they are a bit special. So when a proxy is called, the call itself is non-blocking, so it will return very fast. And the return the value of the proxy is a task result. And the task result can have three different types. It can be a placeholder in the case that we don't have a value for that task. It can, or maybe the task is currently running and we don't have a result for it. It can be a success if the task was completed successfully and we do have a value for it, or it can be an error if for some reason the task failed. The other thing a proxy call does, it looks at the arguments and tries to find other task results that are part of the arguments. If any of the argument is a placeholder, then this means that the current activity or task cannot be scheduled yet because it has dependencies that are not yet satisfied. So it will track the results of the previous proxy calls through the entire workflow, like we can see here. So in this case, when the code is run for the first time in a workflow, the embedded subtitle task will be scheduled, and its result will be a placeholder because we don't have a value for it. But the calls for the video encoding won't schedule any activities because they will have placeholder as part of their arguments, meaning that there are unsatisfied dependencies. And in this case, the results for the proxy calls for the encode video task will also be placeholders. So what this does, it's actually building the DAG dynamically at runtime by tracing all the results from the proxy calls through the arguments of other proxy calls. And finally, workflow finish its execution when the result, the returned value, contains no placeholders, meaning that all the activities or all the tasks that were needed to compose the final result are finished. And like you can see here, this is true for even for data structures. So we have here a tuple, and the values are inside the tuple, and this will continue to work. And the timelays there are in a list, and those will also get picked up. So you can use any kind of data structures for the return data as long as it can be JSON serialized. That's what it's used for serialization. So there are a couple of important things to mind when writing a workflow. Basically, what you want is for all the decision executions to have the same execution path in your code for the same workflow instance, right? So for all the decisions that belong to the same workflow. This usually means that you have to use pure functions in your workflow, or if you want some kind of side effects, either send those values through the input data to the workflow, or have dedicated activities for them, or dedicated tasks for them. So the other thing you can do with the task result is to use it as a Python value. Like we see here, I'm squaring two numbers and then I'm adding them together. And when this happens, if any of the value involved is a placeholder, meaning that there is no result for it yet, a special exception is raised that will interrupt the workflow, the execution of this function. So in effect, this acts as a barrier in your workflow, and it won't get passed until you have the values for the results that are involved. This also means that if you have code after this place that can be concurrent, it won't be detected. So you have to make sure that you access the values as late as possible to have the greatest concurrency. A similar thing happens in the original code of the example, where we iterate over the chapters that are found in the video. So here too, this acts as a barrier, but being at the bottom, it didn't affect the rest of the code, so you may have not noticed it. Another example is when you have a situation like this one. So here I'm squaring two numbers, and then I may want to do some optional additional computation, and it's not clear in what order the if conditions should be written, because if in this case, if the B computation, so squaring of the B is the first one to finish, because I have the conditional on the A value, it will have to wait until the result for A is available to progress further in the workflow. And no matter how I try to write the code, there will always be a case where the workflow cannot make progress until the other value is available. And this is kind of a problem, but it can be solved with something that is called a sub-workflow. So here I refactored the code that did the processing for each number in part in a sub-workflow. And then in the main workflow, I'm using the sub-workflows as I would use a regular task. And this way they can all happen in parallel. And when both are finished, I can sum them and return the result. So workflows are a great way to do more complex things that you couldn't without them. And another thing to notice here, in the main workflow, I didn't have to do anything special to use the sub-workflows. They are used just as regular tasks. So for error handling, you might expect the error handling to look something like this. This is how a normal Python code would look like if you had some exceptions in a function. But this is not possible because, as I said earlier, the proxy call is non-blocking, so you cannot get the exception at this point. So actually, this is the place where you have to write your try except clause. So the reason for this is because only at this point we can force the evaluation of the result, and only at this point we know for sure if the computation was successful or not. And this looks a bit strange, and I don't like it too much. There is a better way of doing it using the wait function that comes in Flowy. And what this does, it will try to evaluate, to dereference the proxy, the task result, and it's similar as doing an operation on it. And the name is a reminder that this will act as a barrier, so nothing will pass this point until, and not only that it won't pass this point, but won't be detected even if it could be executed in parallel until this value is available. But this is not always the case. You are not, you cannot, maybe you don't want to use the value in the workflow itself, you just want to pass the value from a task to another task. And in this case, how do you pick up errors? So what would happen here if the result for B is an error? When you're passing an error in the arguments of another proxy call, the proxy call will also return an error. So the errors propagate from one task to the other. And if the result value that you try to return from the workflow contains errors, then the workflow itself will fail. So you cannot dodge errors, you have to deal with them, or you can ignore them by not making them part of the final result, in which case you will get some warning message that you had some errors that were not picked up by your code or handled. So The workflows can also scale by using some of the other backends that I mentioned earlier, the Amazon one or Eucalyptus. And there are, when you want to scale, basically nothing changes in the workflow, so you would still use the code that you saw earlier. There are some additional configurations that you have to do that happens outside of the code, so are not part of the code. Because when you scale and you want to run the workflow on multiple machines, in a distributed system there can be all kinds of failures. There are some execution timers that you can set, and those will help you with fault tolerance. There is another type of error that you can get when you scale, which is a timeout error, which is a subclass of the task error that we saw earlier. So you can have special handling for timeouts. There is automatic retry mechanisms in place, and you can for the timeouts, and you can configure them as you wish. There is also the notion of the heartbeats, and the heartbeats are some callables that a task can call. And what it does when a heartbeat is called, it will send a message to the backend telling the backend that the current task is still doing progress. But another thing that it does, it will return a Boolean value in the task, and that Boolean value can be used to know if the task timed out, in which case you can abandon its execution, because even if it finishes the execution successfully, its result will be rejected by the backend. Another thing to keep in mind, you should aim to have tasks written in such a way that they can run multiple times, just because of the failures that can happen and the retries. The tasks or the activities, I'm using they mean mostly the same thing, can be implemented in other languages, so you can use Flowy only for orchestration and workflow modeling, so the engine and the logic to run the activities. There are some restrictions on the size of the data that can be passed as input or the result size. Each worker, so when you are scaling and you run on multiple machines, you would have workers that are running continuously, not like we had for the local backend where they were running only for the duration of the workflow. And those workers are single-threaded, single-process, so if you want more of them on a single machine, you have to use your own process manager and start them and make sure that they are alive. And if the history gets too large, so the decision must use the workflow history, the workflow execution history, and the workflow state to make decisions. And if the history gets too large, and actually the history, the data that is transferred because of the history has an exponential growth, you can reduce that by using sub-workflows. Sub-workflows will only appear as a single entity in the history, so they will you can get basically logarithmic data transfer by using sub workflows in a smart way. And because of the fault tolerance built in, you can scale down. So you could, like for example, all the workers can die at some point in time, and then after a while they would come back online, and the workflow progress won't be lost. You may still lose the progress on specific tasks, but the workflow itself, the workflow progress won't be lost. And this is very useful for workflows that take a very long time to run, I think the maximum duration for Amazon is like 1 year for a workflow, so this can be very useful in some situations. And you can also scale up very easily. Just start new machines and they will connect to the queues and start pulling tasks that need to be executed. Thank you. That was all. If you have questions, I think now it's a good time.
How does this compare to Celery? There is Celery, you can create tasks and it will automate them. How can you compare it?
Yeah, so with Celery, so Celery is a distributed task queue or job queue. And it's a bit different because here you have the orchestration of the tasks. So if you have many tasks and you want them to operate in a certain way with some dependencies between them and to pass data between them, you can do that by writing single-threaded code. And from that single-threaded code, the dependency graph will be inferred for you, and it will make sure that the tasks are scheduled in the correct order and they get the data they need passed in. So I would use Celery for one-off jobs, sending an email or something, but not for hundreds of jobs that are somehow interdependent.
Celery also has Canvas.
Yeah. Yeah, it also has Canvas, which is more like a DAG, where you define your workflow topology before, not in such a dynamic way you can do with single-threaded Python code, where you can have conditions and for loops and all that.
Thank you. What asynchronous library you use as a bottom of the Flowy?
Sorry.
Sorry.
What async lib?
Asynchronous library. AsyncDB, Asyncio, maybe Givent.
I don't think I'm using any asynchronous library. For the local backend, I'm using the futures module to implement the workers, but there is no asynchronous library involved.
Okay, thanks.
Yeah, in the example workflow, you showed one of the tasks returns the list, so the list of chapter points that then gets fed into something that builds thumbnails for the chapters. Do you have to wait? Does that task essentially block until every single chapter has been found? Or would it be possible, maybe with code changes, to support, say, a generator function so that you could start building the thumbnails for the first chapter while the task is still finding the later chapters?
So here, so here it will block. So any code under the thumbnails line won't be executed until we have the chapters. And this is because the find chapters returns a list. And it's a single result. And we cannot get partial results from the task. So we have to wait until the entire result is available. Yeah, so anything below that will be blocked until the result is available. And this isn't such a big problem usually because there are ways to write the code and this doesn't become a problem. Or if it is a problem, you can create a sub-workflow. So I could have a sub-workflow that would do only the find chapters and the thumbnail generation, and then call the sub-workflow from here and have that running in parallel with the other code.
Sorry, just to follow up then. Does that mean that in this example, add tags, which you could start processing immediately, won't be executed immediately because you're waiting for the video encoding to finish?
No, in this case, in this example, all the tasks that can be executed in parallel will be executed in parallel. So the actual execution topology will basically look exactly like this one. So this is how it will get executed. That's why the workflow duration was about 2 seconds instead of 11 or something.
The time for the last question.
Kind of a repeat of the previous one. He made a good point about not the thumbnail line, but the line above where it's finding the chapters and returning the list. It won't return from find chapters until it's found all 3 of the chapters. But could you convert find chapters to be a generator or get it to return next chapter, and then you can do the thumbnail for the first chapter while find chapters is still finding the second chapter.
So yeah, you could have a task that will only find the first chapter and return that, and then call the task again, and it will resume from that point. You can actually send the last chapter and find the next one. And this way you can solve the problem if you want to. So it really depends on how you write your code. The only rule you have to remember is that when you try to access a value in the workflow, it will block until the value is available. That's basically the only thing you need to know. Anything below that point won't be detected and cannot be concurrent, and that can be solved through sub-workflows.
Sever, thank you very much for your talk.
Thank you.
We have now 5 minutes break, and then Kyle Knapp is going to talk about porting Python applications to any environment.
Yeah. Hi, Miro. Yeah, good to meet you.
Amazon. That's where I bought one book last week.
Nice.
You know how it goes, like I will show you 10 minutes before. Do you want some answers, questions, answers?
My talk's probably going to kind of cut toward the 30-minute borderline, so I'm going to probably have them just ask questions on the side.
Okay, I will show you.
Yeah, just kind of.
Should I present you some?
Yeah. Is it a hard cutoff if I can hit the very deadline of it? I'll try to cut.
I will show you 10 minutes before, 5 minutes before, and then I just
cut this off. Okay. All right. Cool.
Well, also, if I will work with the microphone, so if someone wants to ask a question, if anyone would not want to be interrupted during the talk.
Yeah, I don't want to be.
Okay, so you are not going to be interrupted. And afterwards, I try to go with the microphone to the person. If someone asks without microphone, it goes very quickly, and then someone, please repeat it because other than that.
Yeah, I have a feeling I'm going to be cutting it really short there. So.
But you have more experience than I do with talks.
Okay. You need to figure out how to get this thing to work. So.
Okay. I see Macintosh. I probably cannot help you.
Yeah, I'm just. I tried it before. It wasn't. The screen wasn't really working too well, but I think I have an idea.
You use more power. More power. Always more power.
Yeah.
start.
Cool. Yeah, okay.
Does it work on your
Yeah.
the microphone?
Yeah, sure. That'll be great. Why not?
Super. Works. So then you can move also a little bit.
Yeah, all right.
I have a microphone just to talk with the people.
Yeah, okay. Cool. Test.
I see a sea of green chairs or seats in the middle. Could you please push a little bit so there, if other people arrive later, so they don't have to climb over your heads? Thank you. Okay, so I hope Kyle already prepared his presentation and it will work on his computer.
Yeah, hopefully.
So let me introduce Kyle Knapp is going to talk to us about how to port Python applications to any environment. Here you
Cool.
go.
All right, hi everyone. My name is Kyle Knapp, and I'm a software developer at AWS, where I primarily focus on developing the AWS Python SDK, also known as Bodo, and the AWS CLI, which is a Python-based command line interface for managing your AWS resources. And this is my talk. It works on my machine, writing Python code for any environment. Well, that graphics must be there. So does this look familiar where that you start developing on your own machine, and it works fine, and so you decide you're going to push it to another computer, say it's a server or a GitHub repo or another colleague that might be using it. There's supposed to be a graphic that kind of goes around showing it fails at the end once you get the success, but let's see how that works. Okay, so you may be wondering, why does compatibility matter? If it works in my environment, why would I care that it works on somebody else's? Well, if you ever want to adopt more users for your program, most users are not going to be running it on the same environment as you. They're going to be using a different Python version, a different operating system. And therefore, it's important that you could be able to run it successfully. Secondly, usability helps drive popularity. When there's no barriers to entry to actually use your program, it helps widen the range of possible users. Many popular Python programs out there, such as Django, Flask, Request, they all have compatibility across a bunch of different operating systems and Python versions. And finally, most of the time, it is not difficult to ensure compatibility across the different environments. Oftentimes, it's just a line here and there. Oftentimes, a couple times, it's a little bit more difficult. But let me go over what will be covered in this talk. First, going to go into background about a sample application that most of the topics are going to be based around. Then I'm going to talk about the different Python versions and how to ensure compatibility across that. I'm going to talk about how to get compatibility across operating systems. And finally, how to write tests to ensure compatibility and help improve it. So the sample application I'm going to be talking about is the AWS command line interface. Like I said before, it's a Python-based CLI used for managing your AWS resources. I decided to choose this application because I have a lot of experience with it. And in the end, it's a CLI. Most users are not Python developers. They're not concerned with what Python version they're running or the operating system. They just want it to work in the shell. And so many of the topics I'm going to cover are based from my experience working on the CLI. The AWS CLI is compatible on Python versions 2 from 2.6.5 and higher, and Python 3 versions 3.3 and higher, and is also compatible on a bunch of different operating systems, such as Linux, Mac, Unix, and Windows. So the first topic I'm going to cover in terms of compatibility is Python versions. Some of the subtopics I'm going to cover are renamings, the differences in string types across Python versions, and the possible limitations you may run into. So with renaming, a lot of times when you're working with across Python major versions, the modules or the classes or the functions may be renamed. And whenever developing on CLI, I sometimes run into this. And the question you may be asking, how do you handle that renaming? The most general solution is to use Six. Six is a compatibility library to help you write Python code that's compatible across Python 2 and Python 3. And it will handle a lot of these conversions for you. So here's an example. The class string.io, which is a class that wraps data into a file-like object. In Python 2, you import it from the string.io library. But in Python 3, you import it from the IO library. The issue here is if you wrote a Python 2 style of formatting it, and you ran on Python 3 code, you'll get a bunch of import errors. But fortunately, the solution is quite simple, thanks to Six. You can just simply import string.io from the Six library. However, this brings up the edge case of what happens when there's no Six compatibility. For example, in the CLI, we have to use the format date function, which is a function that returns a string in the form of what you expect to see in an email. In Python 2, you import from email.capital-utils, and from Python 3, you import it from lowercase utils. And like I said before, there's no Six conversion for it. So the solution to that is to have your own compatibility module to handle all these conversions. And a lot of the projects I work on, it's called a compat.py file. And simply you just have this logic. First, you check to see what the Python version you're working on. And if it's Python, for example, if it's Python 3, you import the Python 3 version of importing format date. And if it's Python 2, you just do the Python 2 version of it. Then to build on top of that, whenever you need to actually use format date, you just import it directly from the compat module. Note that it's a lot better to use the bottom way of importations instead of having this code block and every single file you need is format date, because if you ever want to change the logic, you'll have to change it in every single spot. So the lessons learned here is use Six. It's great for handling all those name changes across Python versions. And if you can't do it, use the compat.py file. So now we've talked about renamings. There's also string type differences across all the different Python versions. So you'll get a change in name and also a change in functionality that you actually will have to handle. So in one example of how to handle string types is input to the CLI. So with input to CLI, we'll have a bunch of different types of input we could be receiving. And here's an example of a CLI command. So we're trying to run the ec2 describe regions command, which will just print out what regions are available for you in ec2. And the input we apply is regions names, the value being US West 2. Underneath the CLI, it uses the argparse library to create a namespace of all the inputs that got received. And inside of this namespace, the values may differ, even across string data types. So across different Python versions, you can have different string types. So I keep talking about this Python string type, so let me cover them now. There's two ways to represent Python strings. There is string data represented as bytes and string data represented as Unicode. In Python 2, the string class is string data represented as binary, and Unicode class is string data is represented as Unicode. And then this changes, though, in Python 3. In Python 3, bytes is the class that represents string data as binary, and string is the class that represents string data as Unicode. So that can be kind of confusing right off the bat. To put more on top of that, there's different functionality between the two Python classes, or Python versions. So for example, if you try to mix the two different string types, and here we're trying to concatenate a byte string foo with a Unicode string bar, Python 2 will do some implicit decoding for you such that when you concatenate the two together, you'll get the Unicode string foo bar. by decoding foo first and then adding the two together. However, this can cause issues for you. If you take this example right here, where you take the byte string E2 and concatenate with this Unicode string bar, you'll get decoding errors where it tries to decode the E2 byte string, but it can't because it's ASCII, and it's out of range. In Python 3, it's a little bit more strict on how to handle this. So if you take the same line as before, you'll just get the error. You can't concatenate bytes to string straight up, and you won't have a vague message. So the problem here is, how do you handle this, especially when you have no control of the inputs that you may be receiving, and you know that mixing string data types is not good. So the solution that I've found through my development is to ensure that the string type consistency is consistent right off the get-go for input to your program. So take this method, or this method that we use when we receive an argparse namespace. The method parseNownArgs takes a namespace here. It first determines what the terminal encoding is being used for standard input. And then what it will do is it'll iterate through each namespace that was provided and to determine if there's any string binary types. So for example, here we're using 6, which has a useful helper method that determines if the string data is represented binary depending on what Python version you're running on. And if it is binary, we determine to decode it to a string data type represented as Unicode, such that any string data type in the namespace is represented as Unicode. So lessons learned here is that Python strings differ semantically and functionally, and you do not want to mix the string data types, especially in the bowels of your project, because it can be very hard to trace back what happened, what went wrong. And to do so, make sure you ensure that the type is going to be consistent as soon as possible. So I've been talking about a lot of these renamings and changes of functionality, but what happens when the functionality straight up doesn't exist? When developing on the CLI, there's a couple occasions where there's no functionality, especially for Python version 2.6. And our solution to that is to actually backport the functionality. An example of a backport is the orderDict class. It's an order dictionary that keeps track of when you insert your keys into the dictionary. It's in Python 2.7 and higher, but not in Python 2.6. And we don't add this functionality from scratch. It's a pretty large class to be writing by hand. So how would you go about doing this? First, you would want to add a conditional dependency. Fortunately, there's a third-party package that implements orderDict for us, and we can pull that in as a conditional dependency. So take this snippet of code from our setup.py file, and we take our original requirement, or our normal requirements, and then we use the sys.version.info tuple and determine if the Python version is 2.6. And if it is, we'll actually append this new conditional dependency into the requirements. Then the second step, in order to hide the lack of functionality, is to import it using the compat.py file. In this case, here's an example snippet where we first try to import orderDict from where we expected it to be if it was Python 2.7, which is the collections library. And if not, we'll import it from the third-party package that we pulled in. So the lessons learned is you may need to backport when needed, but you want to make sure you limit the effect on untargeted Python versions, especially with the dependencies. You want to make sure that you are not pulling in an unnecessary dependency, especially for like Python 2.7. You don't need orderDict because it's already in the library for you. So next, I'm going to talk about operating systems and how to get compatibility across all the different a bunch of different operating systems you may run into. So the first topic I'm going to talk about is file handling. Then I'm going to talk about how to handle file paths, and then finally functionality and lack of functionality, or how it may differ across operating systems. So file handling, most likely if you have a Python application that you're going to have to deal with files. The interface for files across operating systems is pretty similar. You pretty much can open up a file with read or write or in bytes, but it's really the undocumented functionality that you got to be aware of that may be a limitation on the operating system. So for my introduction for this, I'm going to talk about the AWS S3 CP command. What this does is it uploads files from your local file system to Amazon S3, which is Amazon's storage service. And you similarly can download files from S3 and copy it around your buckets. And when it runs this command will work in parallel. So it makes a request to S3 in parallel and does all the writing and stuff like that. So the original implementation of how we did this was we would have multiple threads. In this case, let's say 3. We would make concurrent requests to S3 where we are doing range gets for a specific object. And once each thread will get their data, they will then write to the specific point in the file. Note that they know exactly where to write, saying that is a range get, so they can seek to where they want to in the file, and they know how the content length, so they know when they're done writing. Thus, each thread won't be corrupting another part of the thread's file. However, we ran into problems with that, where if you start with a brand new file and you try seeking to it, the operating system will extend the file with a bunch of zeros. And when you're extending the file and writing to the same time, some versions of Windows we've found does not have support for that, or there's limitations in it, and what happens is we get corrupted files. So our solution to that was to add an IO thread to limit the amount of concurrent interactions with the file. Here we take the normal 3 threads, and they pass on their data to this IO thread, which will then sequentially write the data to the file. Note that the bottleneck here is not at the IO thread, as making the request across the network and retrieving the data is much slower than writing it to the file. So the lessons learned here is that file handling behavior, it can vary greatly, or not greatly, but it can vary subtly, and you need to be aware of it. And also, in order to help cover these undocumented behaviors, is to limit the number of concurrent interactions you may have with a file. So I didn't cover all the other issues we've ran into, but one example is if you have a file open and you try to remove a file handle open and you actually try to remove it, you'll get a bunch of tracebacks on Windows. So the best way to avoid all these is just to limit how many interactions you may be having. So if you are handling files, you're most likely having to deal with file paths and how the location of files represented. So for the intro, I'm going to build off my previous example with the AWS S3 CP command, which has a recursive option which lets you upload or download a whole directory to S3 and back. It relies on being able to list files. The problem is file paths differ across operating systems. So for example, if you take Linux, if you get the current working directory, all of your paths will have a separator of a /, but for Windows, it'll be backslashes. And the way S3 is represented in the CLI is the Linux version. So for example, if you take this here where you have a local Linux machine and you're transferring a file to S3, if it's located underneath my dir with the name my file, if you want to transfer it to S3, you don't have to worry about any renamings or anything. It'll just transfer just fine, where the object in S3 will be named my file and have a prefix of my dir. However, for Windows, it's a little bit different. Note that in Windows, it's a /, and thus, in order to handle it, you actually need to you normalize the separator in this case. And that allows you to transfer to S3 and still have the same the desired functionality of having a prefix my dir with the name my file. So the general solution to handling these is to use the OS library. There's a lot of neat functionality that will let you handle a lot of these things that you may run into. For example, for the example I just provided, if you can use the os.sep property, which will determine what separator is used for your path, and you can replace it with a normalized version, which was a / in my example. So the lessons learned here are files can be represented differently across operating systems, and you want to be wary and use OS whenever you're handling file paths, because if you have a hard-coded value in there, it will mess up your Python program. And then finally, like I talked about across major Python versions, I'm going to talk about differences in functionality across operating systems. So, given one example of where we ran into differing functionality across operating systems is with the CLI help command. So what the CLI help command will do is if you type on the command line just any command plus help, you'll get a man page that shows up, and the man page will let you scroll through it and it'll collapse as needed. Implementation-wise, all we do is we generate the output, and then we pipe out the output to a pager such as the command line utilities less or more. The one thing you want to note that is less is like more, but has a little bit more functionality. So for example, if you hit the bottom of a page when you're paging, you can scroll back up. So the problem that we ran into was that Linux has the ability to use both more and less, but for Windows, you can only use more. We did not want to subtract any functionality based off the operating system, such as only deciding to use more for no matter the operating system, because Linux has the functionality for less, which is a little bit better pager to use. So ideally, what we want is for Linux operating systems to use less, and for Windows users to use more. So the solution here is to actually have platform-specific code. If you use the platform.system call, what that will let you do is determine what operating system you're running on. And in this snippet, what I'm doing is I'm checking to see if the system is Windows, and I'll return a help renderer specific for Windows, if so. And if not, I'll return a POSIX help renderer. And if you look at these subclasses, the pagers that get assigned to it are what you expect. So for Windows, we have the utility more, and for POSIX, we have less. However, there's a little bit more you can actually apply to this to help the healthiness of your program. Ideally, when you have to overcome these different functionality differences, it's a good idea to follow LSP, which is to make sure that the objects in your group have the same interface, such that any object or function that may be calling these objects can expect a similar interface. So for example, if you take the parent class from the Windows help renderer and the POSIX help renderer, you'll notice that it only has one public method, which is a render method. And the render method pretty much hides all the differences in functionality between Windows and non-Windows machines, and it'll just pipe the output that gets generated to the appropriate pager. So similarly, you can take like the help command that actually runs it, and all it has to do is call get renderer, and it will not have to worry about what operating system it's running on. It'll just retrieve the appropriate class, and then it can just call the render method on it to make sure to actually get it to do what you want it to do. So the lessons learned here are the operating system functionality may differ, and if it does, it is all right to have platform-specific code. But if you are going to add platform-specific code, you want to make sure you create some parity in the public interfaces, such that any compromises you make in one class doesn't affect all the functionality of your other classes or throughout your program. So now that you learned some of the tips and tricks about making compatibility across Python versions, I'm going to cover how to write test and run test to help better your compatibility across the various different environments you may run into. So I'm going to first cover writing test. I can't stress the importance of having a good suite of tests just for the different possible issues you may run into. It's ultimately your safety net, because there's a bunch of different compatibility issues you may run into, and you're not going to catch them all. It's really going to help you. It's really going to help you in the end. Most of my examples are going to be via the unit test module, and you have to remember that all the techniques I talked about before still apply. So if you have source code that's even though it's compatible on a bunch of different Python versions or operating systems, if your tests aren't compatible, they're still going to fail. So it's important to have compatibility there as well. An important note is if you're going to use unit test, it'd be good to pull in unit test 2 for Python 2.6. In Python 2.6, it does have unit test, but the functionality is not the same as for Python 2.7 and higher. So similarly, like how we use the functionality in the compat.py file, we can do it as such here, where if it's Python 2.6, we'll import unit test 2 as unit test, and if it's not, we'll just use the regular unit test module. So best practices. One of the best way to catch if your program is capable to run on a bunch of different environments is to actually throw a bunch of common problem-causing inputs into it and see what happens. For example, if one good value there is Unicode, and it's also note that just making the string a Unicode type is not enough. Even throwing some Unicode values in there is great to determine if your program's going to have any decoding errors and whatnot. Similarly, throwing in some bytes as well is a good idea. You often catch a lot of the different types of decoding errors that you may run into, or if you're mixing in the bowels of your project. Finally, for file paths, it's a good idea to have some nested files in it, such that it has a directory. It's just not just your current working directory. And even throw some Unicode into your files to see how, if you're actually modifying the file paths, how it's able to handle that. So another thing I would like to talk about is file handling in terms of testing. A lot of times there's a pattern where you'll mock out the OS library or maybe the open method in order to create like a file-like object, like a string IO or a bytes IO. Ideally, especially for integration tests, it's better to use actual files because there's too great of a difference in parity between file-like objects like string IO and actual file-like objects. And if your program is using files, it only makes sense to use the real thing. So here's an example of what one of your test cases could look like in setting up a file to use. For example, here in the setup method, what we do is we create a temporary directory, and from that temporary directory, you can add any file you want and write some data into it. And then similarly, once you're done setting it up, any test case can actually run in and use that file you just created for the setup. And then in the end, you can just tear it down. It's a great way to be able to test on the real type of files you'll expect in your program. And then finally, you may run into the situation where you actually need a test for an environment-specific behavior. And ideally, what you want to make sure to do is to share code paths in your test. But when you can't, it's all right to skip tests. To skip tests, you can just use the skip if decorator. In this case, I'm skipping if it's a Python 3 version. And I can also skip if it's a platform specific. So for example, here I'm skipping if it's not Mac or Linux. So you may be asking now, when do I know to skip test? Ideally, skipping tests, you should only be skipping tests if the functionality you expect differs. So like the output differs based off what operating system or your Python version you're using. Or if the functionality just straight up doesn't exist. So if you're testing special files such as symbolic links or socket files on Linux that doesn't have any representation in Windows, it's appropriate to skip here. So to reiterate some of the main points here, you want to make sure that you are testing common trouble inputs to get a realistic idea of how it's able to handle possible issues. Use expected types such as the trouble inputs and actual files. And then Skip only when you absolutely need to, as I said it before in the previous slide. So now that you have your test suite written, you want to know how to actually run the test and make sure it runs on all the different environments that you can possibly use. So one utility to make sure you have in your wheelhouse is virtualenv. Creating virtual environments for specific Python versions is great for when you're developing and testing, such that you know how well it runs for a specific version. And also, here's a couple of tools for testing that is great. Nose is a test runner that can run through your test suite. There's Tox, which you can use it to set up your virtual environments, run your tests, and just tear down your virtual environments at the end, and can do that for a bunch of different Python versions. And there's also PyTest, which provides a lot of similar functionality. So here's an example of a tox.ini file that you can find in CLI, where what we'll do is, all you have to do, it's quite simple. You just have to list the different environments that you want to support. So for example, here we support 2.6 to 3.4. And then all you have to do is to specify what the dependencies are, such as there's a requirements.txt saying what the dependencies for the test are required, and then the commands you want to run. So here we're just running nose to run the actual test suite. And then similarly, we can have conditional dependencies for Python 2.6. And note that there's a requirements 2.6 specifically for the unit test 2 dependency. So finally, you may be wondering how to handle like different operating systems. You only have like access to a Linux machine. How do I make sure that I'm running on a Windows? I would recommend using CI systems. The two good ones are Travis and Jenkins. Travis automatically links up to your GitHub repo, so it can automatically test a bunch of these different pushes that you make and make sure that it's supported across all the different Python versions. And then similarly for Jenkins, what you can do is you can launch like an EC2 Windows instance with Jenkins installed, and you can run builds for your tests based off what recently got pushed to your repo. So in conclusion, some of the major topics that I would like to reiterate is to use 6 whenever you run into a Python compatibility issue, Python renaming, or also determining like what Python version you're running on, or determining what string type you're dealing with. For string types, remember that mixing the two are bad. There's different naming conventions across the major Python versions, and the best way to handle it is to ensure that they're all the same at the very beginning of your program. File handling, one of the major issues we'll run into there is that if there may be undocumented behavior that you may not be unaware of, and the best way to avoid it is to limit the concurrent interactions with it. And finally, with limitation handling, what you need to do is oftentimes just backport the functionality or compensate for the functionality, and then hide it, whether if you're importing it differently or if you are trying to use LSP to hide all the functionality differences. And then finally, you want to also test as closely as possible to reality. This will oftentimes catch a lot of these different issues you may run into. And then finally, read the documentation. I said finally a bunch, but oftentimes it's just a one-liner, and they're saying it's this Python version supported or this operating system supported. It can help you save great troubles the next time you're writing your project. And thanks again. Here is the GitHub repo for the AWS CLI. Here is my profile. I think I'm about over time on the. I've got 30 minutes though. Okay. Yeah, so here's my GitHub repo and my profile. If you have any questions about any of the projects I work on, feel free to ask me. I'm going to be here all week. And thanks again.
So we have now some more time left. Any questions?
I've been using AWS CLI for a while, and I was finding it quite hard to get used to the help, like handling the documentation and what's available on the command line. Because usually when you work on Unix-based systems, then the convention is like -- help at the end of the command to see the actual help, and then man as for manual pages. Is that because of the compatibility with Windows systems that you decided to use like just help at the end and no manual?
For that, it was just, I think it was just the implementation detail. It was like how we decided to design it. I believe we just decided to use help. Just, I mean, Windows doesn't have a man page, right? So having a help is intuitive in that case.
Okay.
There's also the Python Future library. I think it's the alternative to 6.
Yeah, features, yeah.
Yeah, but do you have like how it's compared to 6? I know that 6 is quite old, and
Yeah.
some rumors were that Python Future has some different approaches, I think.
Yeah, for this exam, I was just doing it based off what the CLI and a lot of the projects we do. We just use 6 because it's just a very low weight type of way of handling these compatibilities. And for some of our projects, we actually do use features. For example, for Boto 3, we use features for some of our multi-threaded processes.
What's the hardest to support, like Windows or Python 2.6 or 3 versus 2?
I think it's just, I would say just getting it all working on across all the different machines or different environments just hard. I wouldn't say that one's harder than others. Certainly there's some Python versions that have limitations, Windows have limitations, but it's just trying to get it all to work well, because sometimes you may have logic for one that it doesn't work on another, but then you change it and then it doesn't work on the other machine, and it's sometimes tricky, but it's always doable.
I will ask you a question. If I am developing with some Python library that is in Debian or in Ubuntu in a package, and sometimes they update it, just the package will be updated, and then I am not sure if it works, so I can use virtual env, as you told. There are some Python packages that are dependent on other external packages that are not directly with Python connected, so some C libraries. How would you virtual envilize these packages?
Can you repeat the question? Can you repeat the question?
How would you manage the different versions of Ubuntu or Debian packages that are not Python packages, that are C libraries, that get updated sometimes in the background, and I'm not sure whether I can use it with the new Python package or not.
Usually there's it doesn't have a version strapped to it, so you can actually lock down to a version you feel comfortable with.
Doesn't work always.
Yeah, I am not too sure about that. Yeah, I would just suggest that making sure that you're strapped down to a specific version that you're comfortable with is probably the best way to go about that.
Okay, thank you. Any more questions?
The only problem that I see is that, in my opinion, you need to have a clear idea of what you need to do differently for a different environment. It's not something that is going to come on its own. So how can I know what I need to make differently for a different environment? I mean, Windows works differently from Linux, and 2.7 works differently from 2.6 or whatever. But
yeah.
I don't know the differences, so I cannot foresee them. How can I know them before I have to test them?
Okay. Well, probably the best way to do that is to just, like I said, using a virtual env or spinning up like an EC2 instance it's a great way to just fiddle around with your project as you're developing it to see if there's any issues that you may run into as you are developing.
No more questions? Okay, Kyle, thank you very much.
Yep.
So now you can enjoy your meal.
Cool.
Actually, you have now 15 more minutes, but...
Oh, I like again, the entire lunch? Okay.
I told you that I would show you these 10 minutes before, so not a problem.
Oh, really?